Yes, good morning. Today we want to this class. I hope everyone is fine. Today we want to study about capacitors and capacitance. This is a very important topic. In this topic, we begin by looking at capacitors and capacitance. Sorry, sorry, I have some cough. So capacitors are very important devices that are constructed to store charge when the charge is normally stored in electric field between two parallel plates. Then in this diagram, you can see how the fields are aligned between the charges, the positive charge and the negative charges. Then we can see the formula, how to come up with the capacitance, and this is given by C Q over V, where C is capacitance and Q is the charge in coulomb. V is the voltage. Then in the next slide, we can see the 3D illustration, and you can see how the charge is distributed on this plate of a given area, a meter squared, and you can see it is supplied by a particular voltage. Then in slide 4, we bring in the concept of dielectrics. And dielectrics, you can see these are materials that have a very good insulating properties. They can sustain electric field, and when we put such materials between two parallel plates, they tend to help or enhance the capacitor's ability to store charge. When you have vacuum there, you have this constant which we call permittivity. So permittivity is a very important, crucial aspect uh, of this material that helps to store charge. Then in slide 5, we see a small example where we illustrate how to calculate capacitance of a capacitor. And you can see we have this, when we substitute the formula, we make C the subject, we end up with capacitance. Then in slide 6, in this context, we identify the physical factors that affect capacitance of a capacitor, and we can see area of the plate, we can see type of the electric material, the distance between the plates, and the temperature. So these two factors affect capacitance in different ways. So if you have a larger area of plate, the larger the capacitor. If you have a very good dielectric material, the better the capacitance. If the distance between the plates is small, that means that the electric fields will be concentrated, the better the capacitance. Then temperature. So high temperatures, they tend to damage the dielectric, and for that case, the capacitance will fall down or increase. Then in the next discussion, we look at factors that affect connection, how we connect capacitors. There are two practical ways, either in series or parallel. In this first diagram, we look at parallel connection, and you can see we connect them side by side. And to get the total capacitance for parallel connection, we just add C1, C2 plus Cn to the last capacitance. And another unique thing with the parallel connection is that the capacitance, they accumulate, they add up. So the capacitance, the total capacitance increases. Then we move to slide 8. We look at the practical case where you connect uh, electrolytic capacitors in parallel. And this is now how we run the connection. You can see the positive sides are linked together, the negative terminals are linked together. This is how you can implement parallel connection in a practical situation. Then we move to series connection, and we begin by looking at this diagram. And in this diagram, you can see this is how we connect practical electrolytic capacitors in series. And you can see here you have end-to-end connection. So you can see that. Then we move to the next slide, 10, and in this case, we look at series connection. So you can see the electrolytic, sorry for that mishap, but now, yes, so this is series connection. You can see C1 connection is end to end. And the total capacitance is given by 1 over C1 plus 1 over C2 plus 1. Okay, and you can see we add the reciprocals, the fractions of the capacitance values. And for this case, the total value of capacitance, it tends to fall down, it reduces. Okay, so series connection tend to reduce the total capacitance. And I hope you can see this equation. Then you can see now this is practical case. You have but as to calculate total capacitance for a network. Sorry. So in this case, you have capacitance connected in parallel, and then for this case, you see we can now add 1 over 0.1 plus 1 over 0.2 plus 1 over 0.3. And if you prove this in your notebooks, as you can do it after this session, you can go try yourself, you realize that the capacitance will be more, right? And from this also you can calculate the charge across each capacitance, and of course the voltage drops across these individual capacitors will be the same. Why? Because the series connection. Then we move to the next step, and in this next we discuss about energy stored in a capacitor. And this is normally given by an equation of CV squared, where C is the capacitance fixed for a particular capacitor and V is the charging voltage. And you can see this equation gives us this problem here. If you can apply it, you will be able to get the total energy stored in a capacitor. So as a recap, in this session, we've learned about capacitance and capacitor. We've seen how we define the value of capacitor, and capacitor is normally measured in farads. Are we together? Then we've seen about how the 3D connection, right? Then we've looked at the electrics and how its importance in capacitor. We've looked at how to calculate capacitance. We've looked at how identified factors, three factors that affect capacitance. We've also discussed series and parallel connection of capacitor. So I believe at the end of this session, each of you will be well acquainted and the concepts of capacitor, and we look forward to do a practical case where now you will be measuring capacitors using digital multimeter, and also we'll do a practical case now where you arrange them in series. So I thank you for your time, and I hope in our next practical sessions we'll be able to apply what we've learned today, and thank you for your time.